20,000 revolutions per minute. Say that number out loud and it sounds like something bolted into a fighter jet, not something spinning quietly under the back seat of a family sedan on the school run. But that is exactly what happened inside Tesla's drive unit, and the moment the engineering world understood what it was looking at, something shifted. Not a headline. Not a stock alert. A quiet, uneasy recalculation happening simultaneously in engineering bays at Ford, General Motors, Volkswagen, and Toyota, where teams that had spent decades mastering the internal combustion engine suddenly found themselves staring at a problem they didn't fully know how to solve. To understand why this motor rattled an entire industry, you have to go back to a compromise everyone had quietly accepted as fact. For years, electric vehicle engineers operated under an unspoken law. You could build a car that was blisteringly fast, or you could build one that sipped energy efficiently across long distances, but you could not have both. Push for performance and the motor overheated, demanded bulky cooling systems, and drained the battery faster than anyone wanted to admit. Push for efficiency instead, and the car felt sluggish, gutless, uninspiring. Entire engineering teams built their careers around managing that trade-off rather than eliminating it. It wasn't treated as a technical hurdle so much as a fact of nature, the electric equivalent of gravity. Tesla's engineers apparently didn't get that memo, or more accurately, they refused to accept it. Instead of optimizing around the edges of an old design, they rebuilt the core of the motor itself. At the center of their solution sits a component that sounds almost mundane when you first hear about it, a carbon fiber-wrapped rotor. But the physics behind that description are anything but simple. Inside every electric motor is a rotor, the spinning heart of the machine that converts electrical energy into mechanical motion. As rotational speed increases, the centrifugal forces acting on that rotor become almost violent. The faster it spins, the more it behaves like something actively trying to tear itself apart from the inside out. Conventional rotor designs simply cannot survive extreme rotational speeds. They flex, warp, and eventually fail. Tesla's engineers addressed this by wrapping the rotor in a shell of high-tensile carbon fiber, a material prized in aerospace and motorsport for offering enormous strength without adding meaningful weight. That wrap functions almost like structural armor, holding the rotor's shape together under stresses that would destroy a conventional design. The veteran automotive teardown engineer Sandy Munro, whose firm Munro & Associates has spent years disassembling vehicles from nearly every major manufacturer on Earth, is widely credited with drawing public attention to just how significant this design choice was. When Munro's team took Tesla's drive unit apart on camera, the carbon-wrapped rotor became the detail that kept pulling his focus. For an engineer who has spent a career picking apart the industry's best and worst work, that kind of reaction from Munro is not something manufacturers can dismiss as marketing noise. What makes the design so consequential isn't simply that it can spin faster. It's what that extra stability makes possible. A rotor that can be pushed to those speeds without vibrating itself apart allows for tighter magnetic tolerances and far less wasted energy. In a conventional motor, a significant share of the power drawn from the battery is lost as heat, noise, and mechanical vibration. Tesla's design claws much of that lost energy back, meaning more of what comes out of the battery actually moves the car forward instead of dissipating as waste. The same battery pack now delivers more range and more performance simultaneously, which is precisely the trade-off the rest of the industry had assumed was mathematically impossible to escape. The public got a preview of what this approach could do with the Tesla Model S Plaid, a car that uses 3 electric motors to produce over 1,000 horsepower and reaches 60 miles per hour in under 2 seconds, figures once reserved for 7-figure hypercars built in impossibly small numbers. What made the Plaid unsettling to rivals wasn't just the acceleration number. It was that Tesla achieved it in a 5-seat luxury sedan that could still comfortably carry a family several hundred miles on a single charge. Building something blisteringly fast is one engineering challenge. Building something blisteringly fast that is also efficient, livable, and produced at meaningful volume is an entirely different, much harder problem, and it's the one Tesla appears to have cracked first. The timing of this breakthrough matters just as much as the engineering itself. Tesla has been under real pressure. The Cybertruck, once promoted as a revolutionary reinvention of the pickup truck, has underperformed against the sales expectations Tesla itself set when the vehicle was first unveiled. Reports on registration data have suggested that a notable share of Cybertrucks delivered in certain quarters went to entities connected to Musk's own companies, including SpaceX, rather than independent retail buyers. Add in recurring recalls and a suddenly crowded field of electric truck competitors, and the Cybertruck became less a proof of Tesla's inevitability and more a reminder that even Tesla can misjudge a product. In that context, a genuine hardware breakthrough wasn't just a nice technical milestone. It was something Musk badly needed to reset the narrative around Tesla's ability to out-engineer everyone else in the room. That need for a decisive answer lines up with how Tesla has approached materials science before. When Musk introduced the stainless steel alloy used in the Cybertruck's body panels, he described it not as a supplier part number but as something Tesla itself had engineered and intended to share across products, including SpaceX's Starship rocket. That's the pattern to notice. Tesla doesn't treat breakthroughs as isolated features bolted onto a single vehicle. It treats them as core technologies to be spread horizontally across its entire portfolio, from cars to rockets to energy storage. What should concern competitors even more than the motor's performance is how difficult it will be to copy. Manufacturing a carbon fiber-wrapped rotor at real production volume is a brutal engineering exercise. The carbon fiber arrives as a delicate pre-impregnated tape that must be wound around the rotor core under extremely precise tension before being cured under carefully controlled heat and pressure. Wind it too loosely and the rotor flexes and fails under load. Wind it too tightly and the fibers themselves crack. Miss the curing temperature or timing by even a small margin, and the entire component becomes scrap. Every finished rotor then has to be balanced to a tolerance most factories rarely deal with, because an imbalance invisible at normal highway speeds becomes a violently destructive vibration once the rotor is spinning at 20,000 revolutions per minute. A competitor cannot simply reverse engineer this from a photograph. They would need to rebuild an entire manufacturing process from scratch, absorbing years of costly failures along the way, the same years Tesla has already spent and already paid for. And Tesla isn't stopping at raw performance. The company has stated publicly that it wants the cost of an entire next-generation drive unit, motor, electronics, and gearbox combined, to fall to roughly $1,000 per unit, a figure reportedly several times cheaper than what some competitors currently spend to achieve comparable performance. That kind of cost gap compounds across hundreds of thousands of vehicles a year, giving Tesla room to cut prices and still protect its margins in markets where rivals are barely breaking even. Tesla has also been working to reduce its dependence on rare earth elements like neodymium and dysprosium, materials essential to high-performance motor magnets and whose refining is concentrated in a small number of global suppliers, with production heavily centered in China. That concentration has given a handful of governments outsized leverage over the cost and availability of electric motors built anywhere in the world. If Tesla can build a genuinely competitive motor that requires meaningfully less of these materials, it doesn't just lower costs. It partially removes itself from a supply chain vulnerability that continues to squeeze the rest of the industry. Tesla has pursued a parallel strategy with silicon carbide, the expensive semiconductor material used to manage energy flow between battery and motor, working to design systems that rely less heavily on it without sacrificing efficiency. Meanwhile, the rest of the industry has been struggling just to break even on electric vehicles that, on paper, look genuinely impressive. Ford has built well-regarded models like the Mustang Mach-E and the F-150 Lightning while reportedly losing billions of dollars across its electric vehicle division. Lucid Motors has produced technologically sophisticated luxury sedans while continuing to burn through cash at a rapid pace. Rivian has attracted enormous investor enthusiasm without solving the cost side of the equation. Even established giants like General Motors and Volkswagen have faced software delays and mounting questions about long-term profitability in the EV space. Among global competitors, only BYD has shown it can challenge Tesla at genuinely massive scale, largely by flooding markets with lower-cost vehicles. But BYD's strategy is built around affordability first. Tesla is chasing something more ambitious. Vehicles that are simultaneously desirable, fast, efficient, and cheap enough to produce that the margins fund the next generation of technology. It's worth stepping back here, because the drive unit itself is really a symptom of something larger. Tesla has increasingly stopped behaving like a traditional automaker and started behaving like a vertically integrated technology company that happens to manufacture cars. It designs and builds its own battery cells, its own chips, its own software stack, and increasingly its own compute infrastructure through projects like the Dojo supercomputer, built specifically to process the enormous volume of real-world driving video collected from Tesla's global fleet. Every mile driven by a Tesla owner becomes training data for the systems Tesla hopes will eventually power full self-driving. A cheaper, more efficient motor means more Teslas get built and sold. More Teslas on the road mean more data flowing back into Tesla's systems. More data trains smarter software faster than any competitor starting years later could hope to match, even with unlimited funding, because there's no shortcut for years of accumulated real-world miles. The Supercharger network reinforces the same pattern. What critics once dismissed as a convenience feature for early adopters has become one of Tesla's most durable competitive advantages: reliable, widespread, and simple to use in a way rival charging networks have struggled to replicate. Ford and General Motors have both adopted Tesla's charging connector standard so their own customers can access Tesla's infrastructure, an arrangement that quietly means Tesla profits and gathers usage data even when a rival brand makes the sale. None of this erases the genuine engineering achievement sitting at the center of the story. The carbon-sleeved rotor is a legitimately difficult technical problem that Tesla solved before most of its competitors seriously attempted it, while the rest of the industry was still debating battery chemistry and charging standards. But its real significance isn't the motor in isolation. It's what the motor enables everywhere else across Tesla's business: cheaper production costs that fund faster iteration, more vehicles that generate more driving data, and a self-reinforcing cycle that gets harder to catch with every year that passes. For the engineers at legacy automakers studying that same teardown footage, the uncomfortable realization isn't that they're behind on a single component. It's that they may be behind on the entire foundation their future vehicles will need to be built on top of, and there's no simple way to buy, license, or patent your way around years of accumulated manufacturing experience. You can only start building it yourself, knowing that by the time you catch up to where Tesla is today, Tesla will likely already be somewhere else entirely. Whether that gap eventually narrows or continues widening is genuinely still an open question, one that will play out over years, not months. But for now, the small, unglamorous spinning component that Sandy Munro couldn't stop examining on his workbench has become something far more consequential than a single engineering milestone. It has become a signal, quiet, technical, and easy to overlook at first glance, that the old rules electric vehicle engineers once treated.